Let's have another example here. So number 4, find the limit of tangent theta all over sine 2 theta as theta approaches 0. So if we're going to determine the function of theta in this function, that would now be equal to tangent of 0 all over sine 2 of 0. And if we're going to evaluate this one, this is equal to 0 over 0, and that is also indeterminate. Right? So this is a trigonometric function. So we're going to need our knowledge in trigonometric identities in order for us to manipulate this one and to obtain a limit for this function. So this would now be equal to the limit of tangent theta all over sine 2 theta as theta approaches 0. Now, there is an identity for sine 2 theta, which is actually equal to 2 sine of theta cosine theta. Right? So, this is sine of twice an angle, and that is equivalent to 2 sine theta cosine theta. So, if I'm going to substitute this one here, we'll now have the limit of tangent of theta is also equal to sine theta over cosine theta. So, if we're going to make tangent theta sine theta over cosine theta, we're going to write it here, right? All over 2 sine of theta cosine of theta as theta approaches 0. Now, sine theta in the numerator of the numerator can be cancelled out with sine theta in the denominator, right? And cosine theta in the denominator of the numerator will be multiplied to the cosine theta of the denominator. So this will now be equal to the limit of 1 all over 2 cosine squared theta as theta approaches 0. And if we're going to determine the function of theta in here, we'll now have 1 all over 2 cosine squared of 0. And cosine squared of 0 or cosine of 0, quantity raised to 2, that's equal to 1. So this is basically equal to 1 half. Alright? So just another tip here. Cosine squared of x, this is equal to cosine of x quantity squared, right? Um, and this one, this function or this expression, it is not equal to cosine of x squared. So that is also a common error of students dealing with trigonometric functions raised to a certain exponent. So problem number 5. Find the limit of sine alpha multiplied by sine 2 alpha all over 1 minus cosine alpha as alpha approaches 0. So if we're going to get the function of alpha in this function, this would now be equal to sine of 0 sine of 2 multiplied by 0 all over 1 minus cosine of 0. And this will result to 0 over cosine of 0 is equal to 1, therefore 1 minus 1 is equal to 0. So that means that the limit is indeterminate. So we're going to manipulate this function, right, in order for us to obtain a certain limit for this one as alpha approaches 0. And to do that, we're going to use trigonometric identities again. So this is now the limit of sine alpha sine to alpha. Let me just rewrite the given. So we have 1 minus cosine alpha as alpha approaches 0. Now, sine of 2 alpha is actually equal to, right? So sine of 2 alpha, this is twice an angle. So this is equal to 2 sine of alpha cosine of alpha. And if we're going to substitute this one in here, we'll be having, so that's now the limit of sine alpha multiplied by 2 sine alpha cosine alpha all over 1 minus cosine of alpha as alpha approaches 0. Now, if we're going to simplify this one, or if I'm going to multiply this, we'll now have 2 sine squared alpha cosine of alpha all over 1 minus cosine of alpha as alpha approaches 0. Right? So now, this is what I'm saying when it comes to simplification of rational fraction, right? So you might be thinking of canceling out cosine of alpha in here and cosine of alpha in here. No, you cannot cancel out cosine alpha and cosine alpha here because cosine alpha is not a common factor of the numerator and the denominator, right? Because we have an operation in between. You cannot cancel out common terms, you can only cancel out common factors, right? So before we can cancel that out, we have to manipulate this first. So sine squared alpha, right? So sine squared alpha, that is actually equal to 1 minus cosine squared alpha. And if I'm going to substitute it again here, so we now have limit of 2, 1 minus cosine squared alpha, cosine of alpha, all over 1 minus cosine alpha as alpha approaches 0. And if you're going to notice, 1 minus cosine squared of alpha is actually difference of two squares, right? So what I'm saying is, this is in the form of x squared minus y squared. And the factor of difference of two squares are x plus y and x minus y. So if x is equal to 1 squared and y is equal to cosine squared alpha, therefore the factor of this one would be 1 plus cosine of alpha multiplied by 1 minus cosine of alpha. So this would now be equal to the limit of 2 multiplied by 1 plus cosine of alpha multiplied by 1 minus cosine alpha multiplied by cosine alpha all over 1 minus cosine alpha as alpha approaches 0. Now, what we can cancel out here is 1 minus cosine alpha and this whole denominator. Alright, so we can cancel out 1 minus cosine alpha and 1 minus cosine alpha. Thus, the remainder would now be the limit of 2, 1 plus cosine alpha as alpha approaches 0. So if we're going to determine or solve for the function of 0 in this expression, this is now equal to 2, 1 plus cosine of 0, cosine of 0. And cosine of 0 is equal to 1, so this is 2 times 1 plus 1 multiplied by 1. So the final answer is now equal to 4. Let's have another problem here. So we're going to find the limit of 1 plus 1 over x all over x plus 1 as x approaches negative 1. So if we're going to solve for the function of negative 1 in this expression or in this function, that is now equal to 1 plus 1 over negative 1 all over negative 1 plus 1. And the result of this expression would now be equal to 0 over 0. So it turns out that it is indeterminate. So what we are going to do here is that we're going to simplify this one or transform this in order for us to obtain a limit for this function. And to do that, what we can do here is to make it a simple fraction because we have a complex fraction here. So what we're going to do is we combine this first and then we simplify it to make it a simple fraction. And then we try to determine again the limit as x approaches negative 1. So this is now equal to the limit of, if we're going to make this a simple fraction, the LCD would be x. And the numerator would now be equal to x plus 1. All over x plus 1 as x approaches negative 1. Now, the numerator x plus 1 will cancel out with the denominator x plus 1 because they are common factors. So, if this one is cancelled out, therefore, the resulting function would now be equal to 1 over x as x approaches negative 1. So, if we're going to determine the function of 1 over x, or if we're going to determine the function of negative 1 in here, we'll be having 1 over negative 1, or basically that's equal to negative 1. So the answer to this problem is negative 1. Right. So let's have problem number 7. Now, this could be quite tricky, or you might find it difficult because it involves radical expression, but here's how it is solved. Right? So find the limit of 2 minus cube root of x all over the square root of x minus 4 minus 2 as x approaches 8. So the first thing that we're going to do when we're finding limits is to determine the function of a with a given function. So since a is equal to 8, so this would now be equal to 2 minus cube root of 8 all over the square root of 8 minus 4 minus 2. And this is equal to, cube root of 8 is equal to 2, so 2 minus 2 is equal to 0. All over 8 minus 4 is equal to 4, the square root of 4 is equal to 2 minus 2, so that's also equal to 0. So it turns out again that this is indeterminate. Now, what we can do here is to manipulate this given expression. And when you are dealing with radical expression, sometimes the best way to manipulate rational fractions or a fractions that involves radical expression is to rationalize it. And to rationalize this one is to multiply both numerator and the denominator with the conjugate of the denominator, right? So what I'm saying, so let me just manipulate that one so that I'm not going to rewrite this every now and then. So that's 2 minus cube root of x all over the square root of x minus 4 minus 2. Now, to rationalize this one, we're going to multiply both numerator with the conjugate of the denominator, and the conjugate of the denominator is the square root of x minus 4 plus 2. So, our resulting expression here would now be equal to 2 minus the cube root of x multiplied by the square root of x minus 4 plus 2 all over, right? So if I'm going to multiply this, we'll be having difference of two squares because this one, right? So x, the square root of x minus 4 minus 2 and the square root of x minus 4 plus 2, if we're going to multiply it or expand it, we'll be having difference of two squares. So that would now be the square root of x minus 4 quantity squared minus 2 squared, right? So this is now equal to 2 minus cube root of x multiplied by the square root of x minus 4 plus 2 all over, alright, so the square root of x minus 4 raised to 2, that's equal to x minus 4, right? Because basically the square root and the square root will cancel out with the exponent 2. And minus 2 squared, so that is minus 4. So the resulting denominator here would now be equal to, right, so let me just rewrite the numerator, multiplied by the square root of x minus 4 plus 2 all over x minus 8. Okay. Now, since we have 2 minus cube root of x here, we can treat this one, right? So we can treat x minus 8 as difference of two cubes, right? So the x minus 8, let me just write it here. So x minus 8 can be treated as the cube root of x raised to 3 minus 2 raised to 3. Now, difference of two cubes and sum of two cubes can also be factored out. And the factor, right, so the underlying concept here, if we have x cubed minus y cubed, the factor of x cubed minus y cubed is equal to x minus y multiplied by x squared plus x times y plus y squared. Now, this is different from a perfect square trinomial. A perfect square trinomial is x squared plus 2xy plus y squared. Now, this is called a perfect square trinomial because this can be factored out to x plus y quantity squared. Now, x squared plus xy plus y squared is not a perfect square trinomial. This is a prime expression because the factor of x squared plus xy plus y squared is equal to 1 and itself only. Alright, so do not be confused with the perfect square trinomial and the other factor of this one. Right? So just an additional information, the factor of the sum of two cubes, we have x cubed plus y cubed. This is x plus y multiplied by x squared minus xy plus y squared. Right? So if we're going to use this concept, and if we're going to apply this property in this one, right? So we can have it as cube root of x minus 2 multiplied by, right? So x squared here, our x here is cube root of x, and our y here is 2. So x squared here, so that's now equal to cube root of x quantity raised to 2, so that is x raised to, or x raised to 1/3 quantity raised to 2, so that's equal to x raised to 2 over 3. Let me just write it as a fractional exponent. So this would now be x raised to 2 over 3 minus, that would be plus, right? So plus, because I'm looking at this one, all right? So x times y, so that is equal to cube root of x times 2, and then plus y squared, so that is plus 4, because our y here is equal to 2. All right, so let me just repeat it again for if you did not, if you were not able to follow. So x minus 8 can be written as cube root of x raised to 3 minus 2 raised to 3. All right, why did I do this? Because our aim here is to cancel out. Right? So because there is a factor in the numerator that can be cancelled out if we're going to treat x minus 8 as this one. Right? And our x here, this is now, what I mean is, this is now difference of two cubes. Our x in here is cube root of x, and our y in here is equal to 2. So if we're going to apply this property, x cubed minus y cubed equals x minus y, x squared plus xy plus y squared. And since our x here is cube root of x, therefore, x minus y will be cube root of x minus 2, because our y in here is equal to 2. And x squared, alright, so x squared, that is cube root of x raised to 2. If you're going to convert cube root of x to fractional exponent, that is x raised to 1/3. Raised to 2, so that will become x raised to 2 over 3. This is x raised to 2 over 3. Plus, x times y, x is cube root of x, y is equal to 2, therefore that is 2 raised times cube root of x. And lastly, y squared, that's now equal to 4. Alright? So, since this is now the factor of x minus 8, we can write it here. This is now equal to 2 minus cube root of x multiplied by the square root of x minus 4 plus 2 all over, alright. So this is x minus 8, and the factor of x minus 8 is this one. So let me just write it here. So that is now cube root of x minus 2 multiplied by x raised to 2 over 3 plus 2 cube root of x plus 4. Right? Can I now cancel out this factor with this? Not yet, because they are not yet equal. However, I can bring out the negative sign in here so that it will become negative, right? So that will become cube root of x minus 2. Right? So if I'm going to bring out the negative sign here, 2 will become negative and cube root of x will become positive. So this is now the resulting expression. Multiplied by the square root of x minus 4 plus 2 all over cube root of x minus 2 multiplied by x raised to 2 over 3 plus 2 cube root of x plus 4. Now, I can cancel out cube root of x minus 2 with cube root of x minus 2. Therefore, the resulting function would now be negative square root of x minus 4 plus 2 all over x raised to 2 over 3 plus 2 cube root of x plus 4. And if we're going to insert the limit function here, as x approaches 8, this is now equal to the limit of negative square root of x minus 4 plus 2 all over x raised to 2 over 3 plus 2 cube root of x plus 4 as x approaches 8. Right? So if I'm going to solve for the function of 8 here, this is now equal to negative square root of 8 minus 4 plus 2 all over 2 raised to 2 over 3 plus 2 cube root of x, or cube root of 8 plus 2. Alright, so this should be 8. Let me just erase this one. This should be 8 because x minus 4, alright, so that's 8 minus 4 plus 2, and then x raised to 2 thirds, so 8 raised to 2 thirds plus 2 cube root of 8 plus 2. Then we can use our calculator here. So we can now use our calculator here, right? So let me just uh, do that one. So that's negative square root of 8 minus 4 plus 2 all over 8 raised to 2 over 3 plus 2 multiplied by cube root. Alright, so that's shift 8 and then plus 2. Alright, so the answer is now equal to negative 0.4, or in fractional form, that is equal to negative 2 over 5. So this is now the limit of this function as x approaches 8. Alright, so let's have another example here. Find the limit of sine alpha squared over alpha squared as alpha approaches 0. So basically, this is now equal to sine of 0 squared all over 0 squared, or that's equal to 0 over 0. And this is actually indeterminate. Now, how are we going to manipulate this one in order for us to obtain a limit for this function as the alpha approaches 0? Alright, so what we are going to do here is we're going to let, um, alpha squared be equal to y. And since alpha squared is equal to y, if alpha equals 0, then, right, so then y equals 0. So if I'm going to substitute alpha in here, 0 squared is still equal to 0, so y is equal to 0. So if I'm going to change this one as a function of y, this would now be equal to the limit of sine of y all over y as y approaches 0. Right. So now this resulting function is now theorem number 7 of the limit. So if we're going to go back in our notes here, theorem number 7 states that if alpha is measured in radian, limit of sine alpha over alpha as alpha approaches 0 is equal to 1. So in this case, this is now equal to 1. Alright, so example number 9. Find the limit of sine ax all over tangent of bx as x approaches 0. So if we're going to solve for the function of 0, in this function we have sine of a times 0 over tangent of b times 0. Right? So this is now equal to 0 over 0, or that is indeterminate. right? So how are we going to manipulate this one in order for it to be solvable, or in order for us to obtain a limit for this function? So we're going to use theorem number 7 here because we have sine of ax here. What I mean is, by inspection, you can use theorem number 7, which states that limit of sine of alpha over alpha as alpha approaches 0 equals 1. And how are we going to do that? All right. So we're going to convert tangent b of x in terms of sine and cosine. So this one is sine of bx over cosine of b of x. So this is now equal to, if we're going to um, write it, so we have limit of sine of ax all over sine of bx over cosine of bx as x approaches 0. Right. Now, if I'm going to multiply in the numerator, if I'm going to multiply ax over ax in here, and in the numerator of the denominator, if I'm going to multiply bx over bx, there we'll be having limit of sine of ax over ax multiplied by ax. By the way, I'm not changing the value of the expression, I'm just manipulating it, okay? Because our goal here is to have this general form, or this generality, or this theorem, so that we can solve for the given limit function, right? So all over sine of bx, if I'm going to multiply bx over bx on sine bx, we'll be having sine of bx over bx multiplied by bx all over cosine of b times x as x approaches 0. Now, with the theorems on limits, wherein products and quotients of limits can be solved independently, therefore, we can say that this can be solved as, or this can be written as, the limit of sine alpha x or sine ax all over ax as x approaches 0 multiplied by limit of ax, right? So as x approaches 0 all over limit of sine bx over bx as x approaches 0 multiplied by the limit of bx as x approaches 0 all over, right? That is the limit of cosine of bx as x approaches 0. Now, this is already theorem number 7. And this is also theorem number 7. So basically, this is equal to 1 and this is equal to 1. Therefore, the resulting answer here, or the resulting expression here, would now be the limit of x, what I mean is the limit of ax over bx, right? So because we can also write it as limit of a quotient as x approaches 0 or all over the limit of cosine bx as x approaches 0. Now, x will cancel out because x is a common factor of both numerator and the denominator. Therefore, this is now equal to the limit of a over b as x approaches 0. We're going to treat a and b as constant here because our variable here is equal to is x. So if this is a constant, the limit of a constant as x approaches a, that is equal to the constant itself, so that's a over b. All over the limit of cosine bx as x approaches 0 is actually equal to cosine of 0, and cosine of 0 is equal to 1. Therefore, the answer in this problem is a over b.